So first of all, I would like to thank the organizers. It's been a real pleasure being here, listening to the exciting talks yesterday, this morning, talking to people, and also just being back. I will talk about Rydberg interactions beyond the binary limit in two different systems, and these are two topics that I've never talked about before. It's work in progress, definitely unpublished, so I'm very much looking forward to your comments, your thoughts, and input. So I want to just, maybe on an ironical note, and maybe not quite, start with this picture here of a colony of penguins who live in Antarctica, obviously, and so it's a cold place, and to keep warm, the penguins kind of need to optimize their body temperature. So they have an optimal body temperature, and to make it easier, they form groups. Now, as you might see already in this picture, they don't stand directly next to each other, and this is because they would overheat in this case. And it turns out, as this paper will tell you, that the way penguins optimize their group structure, a colony structure, is that they move along the gradient, or the heat gradient that they perceive, and if they're too cold, they will move up the heat gradient. And if they're too cold, they will, if they're too warm, they will move down the heat gradient. And so it can be shown that this kind of procedure already, if you want to model it, does not only include binary interactions, it also includes three-particle interactions. And so they use that for thermal regulation. So in physics...
Just a second, could you just cut the mic?
The mic.
Oh,
I'm sorry.
Okay.
What does Albuquerque? It's in New Mexico, right?
Yeah, I was confused about this too. But I didn't go to the bottom of this. So, I mean, they have the nicest penguin pictures. So I guess it's a zoo or something. I don't know. So in any case, maybe I should go to something that I know some stuff about. So in physics, three-body interactions appear often as some sort of emergent interactions from underlying two-body interactions. So for example, in the classical three-body problem of...
Can you open the
Switch it on too, yes, yeah.
Up there,
Yeah.
There's a knob here. There's a green.
Great. Okay, so does this work? Okay, great. So you will see that there are three-body terms appearing in this classical gravitational problem if you treat extended objects such as planets, for example, as point particles. So that will induce, to describe things correctly, then you need a three-body force. Also, in nuclear physics, there's a three-body force that binds the nucleus together, and as I learned, it makes up 10% of the nuclear binding energy, actually, especially for heavy nuclei. And then, of course, in quantum physics, there are Efimov states famously resulting from collisions of three particles with short-range interactions and giving rise to an infinite series of bound states. Now, I will talk about different systems and connect back to topics that we heard about yesterday, dipole interactions, and kind of try to, in the spirit of the conference, try to unravel emergent interactions in van der Waals systems. First, looking at Rydberg lattices, and then at Rydberg macrodimers, which are giant molecules, and I'll introduce them later. So let's get right into the matter. So three-body interactions, sorry about that, in Rydberg lattices. This is work I together with Ryan Samajda and Misha Lukin. Okay, so looking back at van der Waals interactions, where do they come from? Just a quick recap. Let's say we are looking at two NS states here, and we have this dipole interaction here in the near field limit, so no retardation that we heard about yesterday. So what do these systems do, or what? There's no first order interaction, but instead there's a virtual transition to some other p states, so it could belong to a different quantum number, and prime and prime prime, and back. And so what I want to draw your attention to is that what matters here is the energy difference in this virtual process called the first-order defect between the virtual states and the original states. So now that's the more realistic picture. I'll simplify this to just keep it to a simple model here. So we start from some SS state. Now I ignore that the p states can belong to some other principal quantum number. it's some p state and there's a first defect. So binary interactions then are just like a virtual hop, basically going from SS to PP and back. Now if we have 3 atoms, right, like now there's not only particles 1, 2, but also particle 3. Now this state, like in the ground state, SSS state, could hop up on the first with the first 2 atoms. So you can go to this PPS state and back, PSP using particles 1 and 3, or like van der Waals interaction 2 and 3 and back. And so this gives like kind of a sum of 2-body interactions. But then, as you will see, like kind of the same interaction, the same dipole Hamiltonian will actually also induce interactions between the excited states. So for example, if you have virtually excited to the state PPS, then the flip-flop interaction here, 1, 3, can transition you to the state SPP on these states. So there are all of these connections too, and you can already anticipate that this is the origin, like, you know, where 3-body interaction can now emerge from the 2-body, from the underlying 2-body interactions. Now, this has been looked at like back in the day. So the first consideration of this effect goes back to the 1940s to Axelrod and Teller, who wrote that the general interaction of 3 atoms in their S states in a simple model takes this form. And you see here already that they're always like kind of the dipole, the action of the dipole operator appears 3 times in the denominator. So it's a perturbative, it's a small effect. Then much later there were there was a discussion in the literature around like 2010, 2015 about Borromean reactions where 3 p states can come in and they react to 2 s states and another p states, but only in the presence. I mean, like, you cannot just subtract this from both sides of the equations. Only in the presence of this additional Rydberg atom can this reaction occur. And then Thomas Pohl and others have like looked at Floquet engineering, so driving with Rydberg fields, you can also try to manipulate this interaction. So we will take a different route here, a slightly different route, and look at the many-body interactions in a simple model. So what I show you here is just the expansion of the dipole-dipole interaction in general, and like you see, like all the pairs of atoms, like their interaction depends on the angle theta that connects them with respect to some quantization axis. And so let's make our lives easy for now, and let's say like all the atoms that we consider sit in a plane, and we choose the quantization axis perpendicular to that plane. So in that case, theta is just 0. It's just pi over 2, and this entire model becomes very simple if we also assume that the atoms are dipole, or like 2-level systems, so we have only one transition, one S state and one P state. And so now looking at this, it's already a non-trivial question to ask about like how large are the 3-particle interactions. We saw that they in principle should be there, 3-particle, 4-particle interactions and so on should also be there. How large are they? And it turns out that like this is actually something that you can look at in perturbation theory. So the many-body interactions can be like using von Vleck theory. You can write an effective theory now for the atoms in the S states. And here you see like these are the van der Waals interactions that we all know. So this is a 2nd-order effect. But now I write this to 4th order, and then you see already on the 2-particle level there's another contribution to the 12th. So this is the 4th-order contribution. This is the part that looks at 3-particle interactions with 3-particle terms of this shape and 3-particle terms of this shape. And in addition, then there are, of course, at 4th order, the first 4th-order terms come in, where particles excite and then hop and then de-excite. So you have all of these contributions, and we see that like kind of as we go higher, this is a perturbative expansion, right? Always the higher order terms are suppressed in the 1 over r, like in the separation between the particles. But on the other hand, you see that there are sums over all combinations of different particles. So while each term in the sum is suppressed in this perturbative expansion, the multiplicities of these terms grow. So you get more and more states of each of these contributions. So here I just want to show you like a little example, like how we understand these or one can understand these systems. So let's say like I have a chain of atoms and I calculate the ground state with respect to this model Hamiltonian, and I calculate an effective theory to nth order. So here up to ninth order in perturbation theory. That's then of course done on a computer. And you see that there's pretty fast convergence for large atom numbers. Now, if you go to other geometries, say a ring or like some atoms in a square, you see that the convergence here is not quite as good. And in particular, when you go to something that resembles a square and like becomes much worse. So convergence is quite slow. So what I want you to take away from this like little like simulate or like model system here is that higher order interactions beyond the two-particle limit are only relevant when the particle-particle separation is very small, or when the connectivity is so like when each particle has many neighbors. And in the typical limit that we have in many experiments, this is not the case. So we're in this limit where particles are far away, there's a low connectivity, and hence the two-particle limit, the two-particle interactions are so good, and that's why we understand most of Rydberg physics just with the binary interactions. Okay, so having said this, let's go back to specifically three-particle actions and look at ways of like how could one enhance now the three-particle contributions that we saw were generically small. And so here's an idea of how one could do this. Let's say like you detune one of the components, let's say the PPS states, you detune that optically, for example, and at the same time you make the hopping rate V1 too large. So now this contribution is suppressed, like the binary contribution is suppressed because this state is detuned, and at the same time, like once a particle virtually hops into the state PSP, through application of the dipole Hamiltonian acting between particles 1 and 3. Now, because this interaction is large, it's likely that it will hop over to this one before going down. And then you have included all three particles, and you have actually reached a three-particle interaction. Now, you can also think about this.
So
Yes?
can I ask, so should I think about all this description like a three-body system, just three-body, or not?
I mean, these are three atoms. I'm showing this for three atoms now, but you can generalize this to many body. It's just a perturbative many-body
Yeah, but the
calculus.
analysis here is on the three-body level.
Mhm.
That's it. Okay.
Yes. So you can think about this as like kind of basically if the interaction V12 is very large, think about this as like some sort of splitting of these two lines that then can interact with the state 1 SSS. Okay. So how could one do this realistically? Because this detuning here, this first defect that I introduced in the beginning, is typically very large, so it's difficult in the lab to just like detune one state. So what we thought about is to just minimize this energy scale in the first place, which you can do by, for example, going to a first resonance or like some atomic conditions where this delta is very small, and then one can think about shifting the state, for example, PPS with an AC Stark shift, and then using a first resonance. And now, like, I'm slowly leaving the model character of the description, going back to rubidium, where we then like evaluate this theory. So in rubidium, there's this first resonance that can be used to just make this delta in general smaller. And then let's say like you can also put in a small magnetic field just so to split some of the degeneracies that are there, even for the two-particle system, but even more so for three particles. Okay, so here, what you see here is a three-particle ground state. So here, 37S, 37S, 38S. And you might say, okay, well, that kind of looks very familiar, right? Like it's just another van der Waals interaction that as the distance between particles 1 and 2 is decreased, just drops here. But in fact, in this calculation, the binary interactions is the blue line. So without real three-body interactions, there is actually basically no interaction. So what happens here is that like a split state from another state comes down, and this is a true three-body interaction thanks to the conditions that we have here. So kind of now how do we understand this the system, and how do we maybe like use it for whatever application we have in mind? So let's think about qubits. So every atom can now be in a ground state or in a Rydberg state. So this would be this S state. So this is the manifold of one Rydberg excitation. Then there are states with two Rydberg excitations, and then there's the state with three Rydberg excitations. So the state with three Rydberg excitations, that's the red state that I showed you on the last slide, and it interacts with this other Rydberg state R prime. And so through this three-body interactions, these states will hybridize and mix. And so let's say like if we're interested in the ground states of these systems, let's say we want to go back to a qubit system. So in this case, one could try to eliminate the state here. And in that way, like you get this very long Hamiltonian, or this very extensive Hamiltonian that has like actual three-body interactions. It also has conditional three-body interactions, and it has like these interesting terms that are conditional spin flips, basically, that only flip the spin when the other two particles are in the Rydberg state, and it has flip-flop interactions that are conditioned on the third particle. So with this, like kind of you see like there's a lot of control in all sorts of parameters. There's the detunings, there's this mixing angle theta between the two lines, and so on. So to illustrate like kind of what we tried to like just distill the first features that we might see in the system, let me put this on a lattice. So let's say like these three-body interactions now act between these three atoms and also between these three atoms and so on. But let's neglect two-body interactions altogether, which we saw in this example were small anyways, and let's fix the mixing angle just as at theta half. So that would mean that we're just exactly at this crossing, which you can adjust experimentally, but just by placing the atoms in the right positions. And so then let's look at the phase diagram. So as a function of the detuning and the three-body interaction V, like what would be the ground state of the system? And the first thing to look at is here the classical phase diagram, where we neglect all the terms that do spin flips, and then you will see that there's like a large section with no excitations. So all the atoms in the ground state, there are three excitations when the interaction basically wins, so like when the interaction makes it favorable for the atoms to be all excited, and then there's a small region with two excitations. Now, Ryan ran some DMRG calculations, including the quantum effects in this model, and you see basically qualitatively it's similar to what we saw classically. So there's a big region with low excitation, so atoms in the ground state, then there's like some fairly high excitation, and then there's this region with two excitations. So like this is how we can think about these phases.
What is the color over here?
The color is n, like kind of n in z direction, like kind of the population in z of the qubits per plaquette, so per triangle. It's maximum 3.
This is 3 atoms.
This is like it's a lattice of 25 atoms,
25.
but I took the average over a plaquette, so it can maximally be 3. And so now we can look at, okay, so one maybe interesting point is here in this ground state, this phase is actually like has one atom that's polarized along Z, and the other two atoms are in a triplet state of a superposition of being excited and not excited, giving the total of 2 excitations on the plaquette. And so now we could like kind of make all sorts of analysis, and we're not finished with this yet, but let's say like we make a cut here through this phase space and go from left to right and look at some other observable, let's say sigma x. So then we see that it comes from like an unpolarized state. It goes to another unpolarized state, but in between, so like somewhere here on the space boundary, you see some sort of polarization in x.
So now you have a lattice,
Mm-hmm.
right? And you assume that you are translation invariant, or
Mhm.
this is for granted. So what I mean is that now you have these plaquettes,
Mm-hmm.
and you assume that it is homogeneously, your spin state is the same in all plaquettes. You assume translation invariant?
Assume this for the DMRG calculation? No, it's a finite size effect, so we actually fix the boundary. So the bound, like this is like kind of the, numerically we see that like one particular state that we fixed on the boundary is the one that is like in
so
the...
I mean, is it obvious that you are going to have just that all plaquettes are the same?
No, not necessarily.
So you have hard walls, really.
It's hard walls, yeah, but
Periodic.
not periodic yet, yeah. Maybe a good point, right? I mean, it's not obvious that it's all the same, to me. And we see that like kind of there are fluctuations here at this, exactly at this phase boundary. So then like one thing that one can also look at is like, you know, just calculating entanglement entropy. So how much cutting the system basically in two and calculating the entropy of the bipartition. And we see that there's like along the phase boundary, there's some entanglement here. We're not quite sure yet like how to interpret all of this, but there's definitely like one point, like kind of where the three phases meet, like kind of with the different numbers of excitation. There's like a lot of entanglement here. And so we're thinking about like characterizing this better, like kind of the quantum behavior, the effective field theory that one can maybe formulate around this point. Okay, so I wanted to show you that there are interesting effects that can happen, like emerge from two-body interactions in Rydberg systems. And now I'll just slightly shift gear and talk about like something that's very much experimentally motivated. So like here I worked together with Simon Hollerith, who did all of the measurements as part of his PhD at MPQ. In Emmanuel Bloch's group. Okay, so in case like we've yesterday like already heard a bit about molecules, but in case you haven't heard this macrodimer story, it's quite fascinating. So let me just give you a very brief rundown. So here we again see like as a function of the separation of two atoms, of two Rydberg atoms, you have these potential lines. So very much like the ones that I showed you already, but like very often you have like lines shooting up with positive, repulsive van der Waals coefficients, and you have attractive lines like the red one here. But unless there's some special symmetry preventing it, then at every, like basically there are no real avoided crossings. So what you really have is a curve like this. And now it looks already like you have a potential minimum here. So like some sort of trap where the two atoms at like some separation could maybe vibrate. And this is actually also what you find. So like you can calculate that there are like these states here, like vibrational states basically of two macrodimers, where the special point is that these macrodimers are almost a micron apart. So they're like, they possess all the properties of macrodimer or like of molecule states, except that they have zero electronic overlap. And so this was also seen like then back in Munich in 2019. As a function of the detuning laser, you see like this super nice, very narrow series of many vibrational macrodimer states. And so now you might ask, like, what does this have to do with three-body interactions? As I promised, I'll get to that point. But at this stage, what a macrodimer basically is experimentally is just a two-body resonance in a quantum gas microscope. So you put a square lattice of atoms into a quantum gas microscope, illuminate, and you see here in the experimental figure or reconstructed that there are pairs of atoms that are lost corresponding to the macrodimer. Now that was the state like a couple of years ago, and in the new iteration of the experiment, the main change was that this excitation scheme was upgraded in such a way that now there's a weak probe laser still going up to the single excitation level, but then now there's a near resonant or even resonant coupling laser that strongly couples this first excited state to the macrodimer. And so the strong coupling here is the new point. So now we're leaving this regime of weak optical probing and entering something where these states can now hybridize thanks to the very strong coupling. Okay, so here, this is omega c, like for a fairly weak value on resonance. So we're directly on resonance and probing here with the weak field. And you see that there's a thin line. And then as the coupling strength is increased, you see that there's like some sort of side peak appearing and like cranking up the power of this coupling laser more and more. You see that there are like these deep side peaks appearing. So one can abstract from this and just see that there like the original peak that one saw in the experiment basically gets split into two peaks, and the separation between these two peaks is just scaling with the field strength of the coupling laser. So that's not that surprising with this factor of 2 here because of the collective enhancement. But now here we're just showing the two peaks that are splitting, but in fact there's also the central peak that still remains. And to understand this in a more rigorous way, like you have to actually go back and think about like how these macrodimers are excited from the lattice. And so in the lattice initially, like every atom is trapped in a Gaussian state that is fairly wide on the scales that we're considering. So here, like kind of the first particle is in a Gaussian state that I indicate in this blob, and the second particle is also in a Gaussian state. So in total, there's just a two-dimensional Gaussian state in the two trap positions. Now it's much more convenient actually to not look at this in the coordinates of the first particle and the second particle, but to look at it in the coordinates of the center of mass and the relative motion of the two atoms. Why is this the better frame to look at? It's the better frame to look at because in an excitation towards the macrodimer, the photon basically has no energy or like no momentum, so it will not move the center of mass. But it will change the relative coordinate that then like makes the macrodimer. So basically, you can think about the macrodimer as a state that in the space of the relative coordinate and the center of mass coordinate has the same profile in the center of mass, but has a much narrower relative coordinate. And in fact, it's also shifted slightly with respect to the origin. So it has slightly smaller relative distance. And now when there's like strong coupling, it's almost like a Fano-like problem where this macrodimer couples to this entire continuum of states here in the strong coupling. Okay, so let's go back to the calculations and the absorption line. So here we see like kind of reproduced in theory what is seen experimentally. So it's strong coupling. There are these side peaks, there's a big central peak, and that's basically it. But now we can, like using this intuition, we can ask like what are actually these states that we're seeing here? And it turns out that in the relative coordinate of the two atoms, now on the left you find a state that takes the wave function of the macrodimer. So we transition from a state where the relative motion of the atoms in the ground state was uncorrelated and basically in a wide Gaussian to something where they are very narrow in the relative coordinate. And the same physics happens on the right. You see that again the particles are in a very narrow state. So the entire motional state of these particles is now confined to the narrow motion. You see that there are some wiggles, and this comes from this Fano theory because they're all the background or like kind of the continuum of free states that matters on this side, but not on this. And in the center, and that's kind of interesting, you have this line here that isn't shifted by the macrodimer, and it actually can be nicely understood now that it has the same motional structure as the trapped ground state, except that the coupling to the macrodimer basically eats out all the contributions in real space where the particles are correlated on a short range. So you get this interesting state where with wide correlations except that the short or general correlations except that the short ones are cut out.
So this is like a sphere, like a repulsive sphere.
It's like,
a hard sphere.
yes, I mean, this is one-dimensional, so it's, yes, so it's like kind of,
Super repulsive.
it has a repulsive, it would maybe appear something similar from a repulsive core, yes. And so now, like coming back to this three-body story, like, yes?
Do you have a sense of why is it asymmetric? Like, if I think of it just like eating away at the center position, shouldn't I expect those two bumps to be symmetric?
Yes, I mean, this has to do with the specifics. There are two things that are not quite symmetric. One is that the binding distance of the macrodimer is smaller than the lattice separation, and the other important factor is that the continuum states, basically the free motional states of having one atom excited in the Rydberg state and one in the ground state, it's kind of like a continuum states of free energy, but they have a lower bound. So unlike in the Fano problem where you have like a flat continuum of states, now you have a lower bounded spectrum and degeneracies. So in combination, that leads to this symmetry. Yes. Okay. I will not go over time. So here, like we have this like a lattice, let's say like a one-dimensional lattice, and the macrodimer can live on these two sides. But why? I mean, it can also live on these two sides, or for that matter, on any other sides. And these configurations are perfectly degenerate. And so now what the light field does, actually, when you go to the strong field, it's not like before that we just excited one of those or this one. The light field can actually induce hoppings between this state and this state. And hoppings is maybe not the best word to describe this process, because you get quantum mechanical superpositions of having this state and having this state. So let's look at this, like how it would this will pan out in spectroscopy. So here's the same spectroscopy signal shown again, but now like I calculate this for 3 atoms instead of just 2, with the entire continuum spectrum included. And the general qualitative features are the same. So you have like this big peak here, then you have 2 side peaks here and there. And now, like for 3 atoms, you see that these 2 peaks actually correspond to quenching the macrodimer in one of the coordinates, but not in the other. So here you have the macrodimer quenched in the first coordinate. Here you have quenched it in the second coordinate, while the other one is wide. And on the right part, where the continuum modes, like again, play a role, there are like some wiggles, but in general, that's the same qualitative behavior. On the other hand, like in the middle, that's the peak where you have cut out these correlations. So the short correlations, the hardcore repulsions effectively, and are left with this. But there's also this very special state on the far left. And that's the state where now the macrodimer is quenched in both directions. So rather than having a macrodimer like kind of quenched in only one, you quench in both directions. And it turns out like we can calculate the state, like kind of the wave function of this state in a simple model. And we find that, of course, the center of mass coordinate is just a bystander, but now we get a product state that the entire wave function of this macrodimer triparticle state is described by the center of wave times the relative wave function, the narrow relative wave function of the macrodimer. So it's a 3-particle state that then has like an interesting electronic contribution that's just a product. And here you see like the macrodimer could be on the left or it could be on the right. But there are also electronic contributions where you just have one excitation distributed over the 3 atoms. Okay, so from this, like we really like now emerged again, like from 2-body interactions, like this very much 2-body potential with the light arrived at these what we call macro trimerons, so particles that are bound by light into a 3-particle molecule. Okay, and this is also seen, like kind of this peak here is not really resolved in experiment, but Simon has made correlation measurements and could show that there's actually an experimental signature of a high likelihood of losing 3 particles on this left edge rather than just 2. Okay, so let me come to the outlook. So like what can we do with this in the long run? So maybe like with better alignment between the macrodimer state and the ground state, can we now look, for example, in the future at higher order correlations where we're not limited to just like 3 particles that are bound, but maybe 4 or 5 particles? What are interactions of these macrodimers? After all, they're in their Rydberg state, so maybe can we get some interesting correlated quantum states on the lattice using these macrodimers? Can we maybe go to higher lattice dimensions rather than just 1? Can we look at triangles, triangular lattices, maybe relating to things that Luis Santos told us yesterday about, and can we look at the motion of these macrodimers? Okay, so I'm finished. I just want to reiterate that 3-body interactions emerge from these dipole-dipole interactions in both the Rydberg tweezer arrays and in macrodimers. And if the penguins can somehow regulate their, and profit from 3-body interactions, maybe we can too, and look at this. Thank you.
Okay, thank you. Yeah, other questions?
So I would like to ask, so in the first system that you showed us, do you have hopping in the lattice? Does the lattice make any...
There's no atomic motion.
Okay. So everything is within a latticite? These 3 qubits, let's say, or 3 atoms, right?
No, I mean, it's an atomic lattice in the sense that the atoms are fixed, so the atoms don't actually move, but an excitation can hop from one side to the other.
I see, okay.
So that, I mean, that's like, of course, that's very important for the dipole-dipole interactions, right? Like when in general, like you have these hopping terms, and that also makes the 3-body.
And also in the G2 correlation that you showed, why you see always bunching, right? As far as I understood, no anti-bunching at all. Why?
I mean, this is okay. So this means like you fix the central element here. So you say like, if I have lost an atom on side I, what's the probability of also losing an atom on side? And here it's along the diagonal, because like for technical reasons, these correlations are always lost along the diagonal. So here, like, what's then the probability of losing another atom along the diagonal? So if you had only 2-particle loss, right, then you would have a very positive correlation. If I lose one here, then I also necessarily lose one either here or here. And this is like kind of the generalization to 3 particles. So losing 2, what's the probability of losing another atom in addition to that? So like real 3-particle loss.
Okay. Thank you.
Oh, yeah, please.
So you showed this entanglement entropy picture before.
Mm-hmm.
So perhaps you said that and I missed it. So why do you have this point-like picture there?
Yeah, I mean, we don't fully understand that yet, but like maybe like this is something that often happens, like at points where 3 phases meet, there's oftentimes like kind of like a...
Oh, so this is exactly where you
It's
have
not...
the triple point there.
It's in the vicinity of that. It's not exactly there, but like probably that is connected to having strong quantum fluctuations there.
Okay, I don't see urgent questions. We have a coffee break now, but before that, we thank you for that